Going into this next chapter, I want to start out by reminding us of an algorithm that I think probably some of us know already, but maybe not everybody knows, or certainly there's a chance that we've forgotten about. This algorithm is very useful for coming up with solutions to systems of linear equations. And it's going to turn out, in linear algebra, there's a lot of linear equations sort of running around under the hood. And so I felt like this was a most natural place to squeeze this algorithm in so that we can make use of it when necessary in the subsequent chapters. So, what are we trying to do here? We're trying to say, given a system of linear equations, we want to systematically find all solutions. Now, it could be that there aren't any solutions. It could be that there are infinitely many solutions. So we want to do this in a way that is as robust as possible. And so I want to illustrate this algorithm kind of with an example so that we can have a jumping off point. No, we're not going to do an entire tutorial. It would take us a good 30, 40 minutes. But let's just see how it works in one example. So here's a system of equations. Let's say we start out with 2x, sorry, why is it not letting me write? Plus y minus z equals 8, minus 3x minus y plus 2z equals, sorry, it seems I managed to lose my example, equals minus 11. And then lastly, minus 2x plus y plus 2z equals minus 3. So here's the system of equations that we're starting with. The first step is we transform this into a matrix by suppressing the variables and also any plus signs. In other words, just extracting the coefficients. So we have 2, 1, minus 1. We draw this vertical line here and 8. And then we have minus 3, minus 1, 2, minus 11, minus 2, 1, 2, minus 3. So over here on the left side, we have the variables. And over here, we have the constants. And it will turn out, after we have gotten through more of chapter 2, you will understand like why I'm doing this, sort of what the magic is that justifies this change of notation. But for our purposes, this is the most convenient way of dealing with a system of equations. And now we have to think about, like, what does it mean when a system of equations is solved? Well, a solution will always look like x equals something, y equals something, z equals something. In other words, when the equations are done, you have, slightly more specifically, you have 1x plus no y plus no z, no x plus 1y plus no z, no x, no y, sorry, 1z. And so, in other words, the ideal situation for solving the system of equations is to do some math somehow so that every row consists of exactly 1, 1 and everything else zeros. This motivates what's called the reduced row echelon form of a matrix. And I'm going to give the definition now. A matrix is said to be in reduced row echelon form when the first non-zero entry of every row is 1. If a column contains such a leading one, all other columns are, sorry, all other entries of that column are 0. The leading ones go left to right. And if there's ever a row of all zeros, put that on the bottom. Okay, so this definition of a reduced row echelon form is suggestive of how we should go about trying to solve the system of equations. Because let's remember, we teach our students how to solve equations that look like this, right? We say that you should add these equations together to eliminate something and then solve. This suggests that there are basically two things that I'm allowed to do with the rows of a matrix because the rows represent the equations. So what are the things? I can add rows to each other. I can multiply or divide by numbers. Although not 0, right? You don't want to multiply by 0 because that just deletes the equation, not something you want to do, and you're never allowed to divide by 0. The last thing is, this is a little bit useful sometimes, but strictly speaking, it's not a requirement as a named rule. But you're allowed to reorder the rows. It turns out that using just adding and multiplying, for example, by negative numbers to get subtraction also, you can derive 3 from just the first two. But so let's see how we can use this to try to systematically solve this matrix. So what we're going to do is we're going to try to copy and paste this guy. And then we're going to try to use our row operations to try to reach a state where this set of rules is enforced. And this set of rules, like I said, it basically tells us what to do. I need to make the first non-zero entry of each row into 1, and then I need to clear out the corresponding column. So if I want to put a 1 in this first slot, I can think of a couple ways of doing that. I'm just looking it over to decide if any particular method seems particularly good or bad. The one that I see is, let me add equation number 2 to equation number 1. And then I'm just recopy this because I'm not changing equation number 2. Sorry. The standard notation is that I should write down the row I'm doing the thing to. So I should write row 1, and then I should write down what I did to it. So for us, row 1 plus row 2 doesn't exactly mean the same thing as row 2 plus row 1. I mean, I know that the addition is commutative, right? We all know that. But the standard is to write the row you're changing first. So I'm going to add row 2 to row 1. I write that first. So I get -1, 0, and then I'm adding 2. I get 1, -3. And now I can use condition or rule number 2 to multiply row 1 by -1 to flip the sign over. Don't change anything else just because why not? Right, no reason to try to do too much. And you see I created this situation where there's now a leading 1 in this first slot, which is what I wanted. Once I have this leading 1, the next rule of a reduced row echelon form was that all the entries of that column have to be 0 other than that 1. So now I can do row 2 and I can add 3 of row 1 to it. And I can take row 3 and I can add 2 of row 1 to it. And that will clear out that column. So this now stays the same. This becomes 0. This stays the same because I'm adding 0. Now I'm adding 3 of these guys here, so this becomes a -1. And if I'm adding 3 9s, I get -2. Then we get 0. This stays the same. I'm adding 2 copies, so that becomes a 0. And then this becomes +3. Okay, so this got us quite a bit of progress because now I can actually see that there is a second 1, which in order to make in the next row a leading 1 appear in that row, I could either multiply row 2 by -1, but this row already looks like perfect. So how about I just take that one? Row 2, swap with row 3. And now while I'm at it, let me take the new row 3 and times it by -1. Just because I know I have to do that anyway. Seems like it just makes life a little easier to do it now. Okay, and we're almost done. Next step is I got to do row 3 minus row 2 because of that leading 1. This row stays the same. This row stays the same. This row becomes 0, 0, 1. And then this is -1. And there, properly speaking, there is one last thing to do, which is take that leading 1 and finish. Let's just kind of do this right here. Make this a 0. And then I'm adding -1. So this becomes 2. Okay, and so if I did this right, then this should satisfy the original equations. So how about we just go check that, and then we'll call it if it's right. 2, 3, -1. Oh, oops, sorry about that. The original system of equations is up here. And so let's just try to take these numbers and just check. If I plug them in, does it work? Obviously, I don't have a tremendous amount of room here because we're hurting for space a little bit, but we can erase this matrix now since we're coming up on the end. And then let's check. So I have 2 times 2 plus 3 minus -1, which is 4 plus 3 plus 1 is 8. Right. -3 times 2 minus 3 plus 2 times -1. This is -6 minus 3 minus 2. So that's -11. It's right. Looking good. -2 times 2 plus 3 plus 2 times -1. This is -4 minus 1 minus 2 is -3. It's right. Okay, very good. So these take a little bit of time to do, so I think I'm going to stop this here. I wanted this to be a quick sort of crash course / refresher in how this algorithm works. There are a lot of things along the way that could like not work out. Like, for example, the numbers might involve like gross fractions, or you can have situations where there aren't solutions. I didn't want this video to be a comprehensive tutorial, but once we start getting into chapter 2, which will be next video, I'm going to be using this more and more, and I'm going to point out, all the little quirks that can come up along the way. So hopefully you have some idea how this works. If this is the very first time you're seeing this, I'll just be upfront. I lifted this example straight from Wikipedia, and then I just checked my work against it to make sure it's right. What you should do is similar. You should just, if you have never done this before, you should go on the internet and like look up a couple of Gauss-Jordan examples, and then just try to repeat this process yourself a couple times. Once you have done it, I don't know, maybe 5 to 10 times, you kind of get the hang of it. It becomes pretty quick. And then it'll become really, really easy to apply it on any specific collection of equations, which is what we're going to be seeing a bunch of in this next chapter. All right, so you guys go do that. Take a little bit of a look at some practice, and then I'll see you guys in just a few minutes in the next one.